Hello everyone, this is Group 17. Today we're going to discuss the constrained proximal policy optimization. We're going to discuss its naive idea and our modification to the original CPPO. So the constrained reinforcement learning addresses a problem with safety critical concerns. So we consider a constrained Markov decision process characterized by several features. We have system state, action, system dynamics. System dynamics indicates that the environment transit to the next state given the action. And the reward signal and cost signal. Here the cost signal can cover several dimensions, so we see it has a dimension of m. Then we have discounted factor gamma and discounted factor mu. So we're going to define the discounted return JR pi. So this discounted return is defined as the expected return from the environment after taking specific action under policy pi theta. And also we see the definition of discounted cost JC pi. It's defined as this formula, and we see that the constrained reinforcement learning aims to optimize the policy that maximizes the discounted return JR pi under the constraint that our discounted cost should not exceed the threshold D. Next, we discuss the key ideas of constrained optimal policy optimization. We see that this CPPO models the policy optimization problem as a probabilistic inference problem. Specifically, it considers the log probability where the current policy is the optimal policy. This probability should be no less than the evidence lower bound, written as a form of expectation. The idea of CPPO is to maximize this expectation. So we see that if this expectation gets close to 0, then this log probability is close to 0 as well. Given that this log probability is 0, the current policy will become the optimal policy. So the general idea of CPPO is to maximize this lower bound of the log probability. So next, we get into the detail of the maximization of the lower bound. We see that it's an interesting story because when we get involved in the KL divergence, the KL divergence is actually a formula related to the policy probability ratio. And this ratio has an optimal. When the current policy is the optimal policy, this ratio equals to 1, which means that V equals to 1, then we get the optimal policy. So given this as a foundation, we introduce V bar. V bar is defined as V minus 1. This transform allows the V bar's expectation to be 0, because as we see that the optimal, if current policy is the optimal policy, then V equals to 1, and V bar is the V minus 1, so V bar has an expectation of 0, which means that V bar is actually a vector from the original point. And we see that here is a norm constraint. This norm constraint is actually from the constraint for the KL divergence from the safety concern. And given this norm constraint and the expectation of this V bar, the geometry distribution of this finite dimension problem can be written as this form. Here, this AC tiled AC is actually from the normalized advantage term for the cost, and this tiled A is the normalized reward term. So another question this CPPO addresses is to enforce the element-wise constraint for the V bar. We see that in the finite dimension problem we discussed before, the element-wise constraint V bar should be larger than the minus 1. And this CPPO proposes a recover step, whereby they consider that if there's a dimension in the V bar which is less than minus 1, then they fix this dimension to be minus 1. After fixing this dimension, they re-explore over the advantage plans consist of the normalized cost advantage term and the normalized reward advantage term. As this recover step fixes all the elements in the vector v bar to be no less than -1, they can solve this finite dimensional problem. Given the value of this finite dimensional problem, they gonna to maximize the lower bound for the probability ratio. And as we discussed in previous slides, this optimum value for the probability ratio should be equal to 1. So the current policy becomes the optimal policy.
In our project, we built CPPO on top of a standard PPO implementation. We replaced PPO's clipped objective with CPPO's inference-based update, including the geometric ratio update and the recovery step. Then we evaluate this reproduced CPPO in a safety-critical environment to study the trade-off between return and cost, and to see whether the recovery mechanism can enforce the constraints without causing large performance loss.
Next, let's move on to modification summary. We are integrating a dynamics model into CPPO. This not only ensures safe exploration but also improves sample efficiency. In naive CPPO, cost constraints are enforced in a reactive manner, only triggered when the agent enters an invisible region. Such post-hoc correction is costly, especially in real-world applications where safety violations are strictly prohibited. For example, preventing collisions in autonomous driving would be very costly. Incorporating a dynamics model enables proactive and safe exploration within CPPO. Moreover, model-free reinforcement learning inherently suffers from low sample efficiency, as it requires extensive interactions with the environment to converge to an optimal policy. By integrating a Dyna-style framework, CPPO can leverage model-based rollouts to improve sample efficiency and explore the environment more effectively. Also note that our approach is inspired by Dyna, which is a reinforcement learning architecture that tightly integrates acting, learning from real experience, maintaining a learn world model, and planning using simulated experience to accelerate policy improvement. The training process involves three interactions: agent training with real rollouts, dynamics model updating using real rollouts, and agent training with imaginary rollouts by the dynamics model. Agent training using real rollouts is a process follows the update style of naive CPPO, where the agent is trained with real rollouts collected from the environment. Dynamics model updating using real rollouts means the dynamics model is trained to approximate the real environment dynamics by minimizing the loss function below. Please note that considering multi-step dynamics encourage the model to learn consistent long horizon transitions rather than optimizing only one-step prediction. Lastly, agent training with imaginary rollouts. It's a process that, starting from a current state distribution, imaginary trajectories are generated by rolling out the learn dynamics model from multi-steps. At each step, an action is sampled from the current policy, and the predicted states used as the next input for subsequent transitions. Please note that to reduce model bias accumulation, the imaginary rollouts are channelcade to a fixed horizon edge. The agent is then trained on these imaginary rollouts, performing policy and value updates in the same way as in real environments. The compounding error emerges as the most critical challenge in the dynamics model rollout. It can grow exponentially when spectral radius of the Jacobian of the true dynamics is greater than 1. To cope with this challenge, we develop a retrieval mechanism where we roll back the policy parameters whenever the loss becomes non-finite. This treatment prevents numerical crashes and stabilizes the training process. Below is a picture of the algorithm framework. You can clearly see the training process during the framework. At line 3, we have agent training using real rollouts, and dynamics model updating using real rollouts are done using at line 6. From line 8 to 11, that's where we do the agent training with imaginary rollouts. And also at line 13, that's where we use our retrieval mechanism for stable training.
So we run everything in safety gymnasium on the point goal tasks. The agent just needs to reach the goal while avoiding hazards. Reward measures progress, cost measures safety violations. Basically, this setup lets us test the return cost trade-off directly. For training configuration, we train for 10,000 iterations with a horizon of 1024. Discount factors are 0.99 and the cost limit is set to 25. We use the same optimizer and learning rate for all baselines. CPPO also has a recovery step to keep updates stable. For deny CPPO, we add a small dynamics model trained on real data. Then we generate short imaginary rollout and treat them like extra training samples. This gives the agent more signal and improves sample efficiency. Model rollout can drift, so errors can blow up. If that happens, we roll the policy back to a safe checkpoint. This keeps training stable even when the model isn't perfect. We compare against PPO lag, CPO, and CPPO. To evaluate, we use standardized return and cost. Higher return score is better performance. Lower cost score means safer behavior.
So this is the main results that we observed towards the CPPO and Dyna CPPO. So from the left figure, we see that Dyna CPPO consistently achieves a higher final return over the environment point goal 1. And for the right figure, we see that Dyna CPPO converges to a lower and more stable cost level than CPPO. So these two figures jointly shows that the dynamic model has a higher expectation to improve the performance of CPPO. However, when we get into the detailed look at the initial training stage for Dyna CPPO, we observe a higher constraint violations. One possible explanation is that at the initial training stage, the learned dynamics is inaccurate to simulate the environment. This is the testing results for all our 4 benchmarks. Specifically, we consider CPO, the PPO log, CPPO, and Dyna CPPO. From this table, we see that CPPO outperforms PPO lag, Lagrangian method, and the CPO. So this comparison illustrates the benefit of augmenting first-order constraint policy optimization. Based on CPPO, we observe that the Dyna CPPO offers the highest return and the lowest cost among all benchmarks. So we see that the lightweight dynamics model in Dyna CPPO provides additional informative gradients. So in these slides, we also provide the video demonstration of Dyna CPPO. So we see that Dyna CPPO successfully cope with the task point goal 0. So we see that this board is move itself around the target. We see this in this video, it doesn't reach the boundary of the area. And this demonstrates the success of Dyna CPPO.
So here is what we found. First, deny CPPO gets higher return. The extra imaginary rollouts give it more learning signal early on, so it improves faster. Second, we do see early cost spikes. That's just because the model is bad at the beginning and makes unsafe predictions. But overall, final cost is lower. Once the model becomes stable, the agent avoids hazards earlier and more proactively than CPPO. Here is the quick evidence. Reward goes higher and the cost ends lower and smoother. The metrics also show deny CPPO slightly better than CPPO on both return and cost. Why does it work? Model rollouts give a bit of foresight and retrieval stops things from blowing up. So in short, deny CPPO learns faster and ends up safer.
On the challenge side, we highlight 3 issues. First, compounding model error in multi-step rollouts is the most critical challenge because multi-step errors can grow quickly even if one-step errors are small. Second, we sometimes get non-finite losses, so we roll back the policy parameters to avoid numerical crashes and stabilize the training. Third, Dyna CPPO has higher early-state constraint violations, since the dynamic model is inaccurate at the beginning and causes higher early costs. For the main takeaways, CPPO already improved the return cost trade-off over PPO lag and CPO. Then CPPO further achieved the best return and the lowest cost among all baselines, and short model-generated rollouts helped improve both the simple efficiency and safe exploration without letting model bias dominate. For future work, we aim to better control compounding model error in multi-step rollouts, evaluate the CPPO on more tasks and seeds, and explore richer model-based components. Under safety constraints, we are still keeping model bias under control. That's all from our project. Thank you for listening.